Hello everyone and welcome to our presentation video. Our topic is blockchain security and scalability. First of all, we are going to introduce the popular consensus algorithms. Then we will demonstrate a case study of selfish mining. And finally, we will talk about the scalability of blockchain. Let me show you some of the most common consensus algorithms used in blockchain technology. The simplest one is the proof of work. In this case, miners compete for mining a new block based on their computational resources. The first miner who finds the nodes that could solve the difficulty will get the right to create the next block and get rewards. In proof of work, the mining capacity depends on the computational power, which takes a lot of time and electricity. This consensus algorithm is vulnerable to 51% attack, where the hackers need to compute more powerfully than 51% of the network to add a malicious block. The second most common consensus algorithm is proof of stake. Unlike proof of work, proof of stake has nodes to put up stakes for the qualification to create a new block. If the node fails to create a valid block, it will lose its stakes. If the node creates a valid block successfully, it takes rewards from the network. In proof of stake, the validating capacity depends on the stake in the network. Thus, it takes less time and electricity than proof of work, and thus it can define 51% attack. Delegated proof of stake is an extended consensus algorithm of proof of stake. Instead of putting up stakes, users can vote for a node to be a witness. The witness is responsible for validating transactions and can get rewards from them. Finally, practical Byzantine fault tolerance is designed for solving the Byzantine fault. The Byzantine fault tolerance is the ability to continue operating even if some of the nodes fail or act maliciously. In this case, a node is selected as the primary node. Others are backup nodes. When there is a request from client, the primary node relays the request to backup nodes. In practical Byzantine fault tolerance, we assume the amount of malicious node is less than 1 of 3. If a proposed block is agreed by the nodes in the system, then the block is the final one. However, PBFT rely on digital signatures and message authentication codes, which takes a lot of overhead due to the huge amount of communication between nodes. For example, in the cryptocurrency networks. These are the 4 popular consensus algorithms in blockchain technology.
Another vulnerability in the cryptocurrency results from a mining strategy called selfish mining, which targets the proof-of-work consensus mechanism. It aims to earn a higher payoff through deviating from the standard mining protocol in order to trick honest miners into performing wasted computations. Here are some examples. We have 3 miners. Harry and Howard are the honest miners, whereas Sarah is a selfish miner. At the beginning, they all mine on the global public chain. If an honest miner finds the next block, they all proceed as normal. However, if Sarah finds a valid block, instead of broadcasting this block, she keeps it private and starts mining on her private branch, while Harry and Howard are still working on the store public branch. Let's say Sarah then finds a second block in her private branch. After that, an honest miner discovers a successor of the public branch. Sarah can now publish her private branch. Since her branch is 1 block longer, by the standard protocol, all miners will adopt this longer branch as their new branch. The block mined by the honest miners will be invalidated, and the revenue of both blocks will be given to Sarah. Now consider Sarah is very lucky to be 3 blocks ahead of the honest miners. For every block the honest miners find, Sarah can reveal 1 block from her private branch. Now there's a tie. Both branches are the same in length from the public's perspective. Hence, the honest miners would choose to continue either of these branches, depending on the order of arrival of block updates through the network. We can see that both Harry and Howard are working on store branches, performing wasted computations. Then, if the public branch catches up to only 1 block behind, Sarah would now reveal her entire branch, which is longer and hence would be adopted by all miners. The other branch would be pruned, and all the rewards would be given to Sarah. Now consider one last scenario. When Sarah discovers the first block in her private branch, Harry happens to find another block after the public branch. Sarah must now reveal her block in order to create a tie. Howard would then choose between these two branches, still depending on the propagation through the network. He may join Harry's side or join Sarah's side. If now Harry finds another block after his branch, the selfish branch would be pruned, resulting in Sarah's effort become wasted. Both the rewards will be paid to Harry. On the other hand, if either Sarah or Howard finds a successor for the selfish branch, the honest branch would be pruned, and the rewards will be paid to the corresponding contributors. Simulation shows that if honest miners randomly break ties, this strategy will gain a higher payoff if the mining power of selfish miners is over 25% of the total mining power. The more the mining power, the more effective this strategy becomes. The threat of selfish mining can be further increased by forming a selfish mining pool, CBO attack, or using more optimal variants of the previous strategy, which leads to the well-known 51% attack or the double spending attack, where the selfish miners can take control of the blockchain system, modify the transactions at will. Hence, countermeasures must be developed to prevent selfish mining from happening. Some techniques are listed below. For example, analyzing forks in the branch history, as the most evident sign of selfish mining is two competing branches. However, if multiple entities form a mining pool and are coordinated by a single administrator, the evidence of selfish mining would be distributed to various addresses, making the detection much more difficult. As a result, further investigation needs to be conducted to ensure that there are no opportunities for the attackers.
I'll be introducing the blockchain scalability. The scalability of blockchain system determines how widely it could be used in real-life application. However, nowadays, how to improve the scalability of blockchain is still a bottleneck. About mentioning blockchain scalability, there exists a trade-off between decentralization, scalability, security, and trust as shown in the graph. This means it's difficult for these characteristics to coexist in a blockchain. Throughput is the top priority that needs to be addressed in blockchains in nowadays. It is to say that the higher the throughput, the higher the efficiency of blockchain system holds. As blockchain is described as a distributed ledger, increasing the number of blocks does not improve the throughput of the blockchain, as well as the consensus algorithm together mentioned previously. It is very difficult to improve the throughput in a blockchain system. Taking the payment system as an example, the current throughput of Bitcoin, that is 7 transactions per second, is obviously lower than most of the existing payment systems like MasterCard can reach about 5,000 transactions per second. The solution of improving the scalability of blockchain is using on-chain and off-chain transaction, and I will introduce sharding for on-chain and cross-chain for off-chain transactions. Intuitively, every step associated with an on-chain transaction occurs on the blockchain, and the state of the blockchain is modified to reflect the occurrence and validity of the transaction. Off-chain transactions are methods that take value out of the blockchain. Sharding-based blockchain is seen as promising on-chain solution to blockchain scalability problems of low performance issues. In general, sharding technology is to divide the data on each block into several small fragments and store them in separate nodes. Each node only accesses and manages its data and runs transactions in parallel. Improvement of throughput is achieved by increasing the order of magnitude of fragments. Cross-chain increases scalability by allowing information in the blockchain to be transmitted and communicated on different chains, converting valuable information on one chain into valuable information on another chain. I'll discuss two technologies currently used, notary schemes and distributed private key control. Notary schemes are intermediate notary to guarantee information between chains. However, this goes against the idea of decentralization of blockchain. While distributed private key control is achieved by using distributed nodes to control the private keys of various assets in the blockchain system, separates the use of rights and ownership of digital assets, so that the decentralized system can safely receive the control rights of the assets on the chain. Thanks everyone for listening.